The first one is given by Cecilie Andersen from University of Bath. Please.
Thank you. Thanks for inviting me to speak. So I'm going to be talking about the Saffman-Taylor problem, particularly in a wedge geometry. This is work I've done collaboratively with a few different people. Bill is my supervisor at Bath. Okay, so to start with, I had a slight bit of technical difficulties about 5 minutes ago. So this is actually a series of pictures, but you can only see the last one, so kind of spoilers already. But what I'm trying to show here is kind of set the scene a little bit about what the Saffman-Taylor problem is. I imagine a lot of people in this room are already familiar with it, but just so everyone's on the same page. The idea here is, here we've got a picture where we're looking at a top-down view of a Healy shore cell. So we've got two planes of glass with a very narrow gap between them, filled with a viscous fluid. That's that clear color you can see. And then here there's a syringe which is being used to inject a less viscous fluid. So that's a green color into the fluid. And basically what happens is, first you're injecting the fluid and the profile sort of spreads outwards in a kind of circular shape. And then very quickly we develop an instability, and this is the Saffman-Taylor instability. And these kind of fingers form on the free surface profile. After a while, the fingers sort of spread out more, and then some of the fingers grow quite large, and they then split into smaller fingers and continue to propagate. And this is called the tip splitting instability. And what we want to try and do in modeling the Saffman-Taylor problem in a wedge, which I'll come to later on, is to capture this sort of tip splitting instability and when it occurs. So to begin with, I'm going to cover the Saffman-Taylor problem in a channel, which is kind of where a lot of the research on this problem began. If you're trying to model the picture I was showing on the last slide, the kind of simplest geometry you can think of is a sort of straight channel. Hopefully might capture some of the behavior we were seeing before. So this is all stuff that I've stolen from Saffman-Taylor's paper in 1958, which is kind of the, I guess, one of the first, or the first paper on this kind of problem. So on the top, you see a picture of an experiment that they've done where you've got this Healy shore cell, which is now an infinitely long channel. You're injecting the fluid from the left, that's the less viscous fluid. And after a certain amount of time, you reach a steady state where you've got a single kind of finger which is propagating along the channel. And the crux of the problem is trying to understand what the parameter lambda is, so the proportion of the width of the full channel occupied by that bubble. And these are some quotes from their paper. So firstly, from the experiments, they see that lambda is pretty much a half on all the experiments. Secondly, they do some analysis, some kind of asymptotics. And what they observe there is that the solution appears to be non-unique. Kind of in particular this last sentence here. And this kind of mystery is summed up in the last sentence where they couldn't quite resolve this, and that's then led to lots of other people working on this problem. So I'll continue to some of the slightly later work and review some of this. So this is the setup I showed on the last slide. We're going to try and model the free surface to try and identify what this parameter lambda is. We've got two key variables, which is the q and the tau, the speed and the angle on the free surface. And then you've got a parameter zeta, which is going to parameterize this free surface in this problem. The governing equations you can write down are in this top right. So the first equation is Bernoulli's equation, which is essentially a pressure balance on the free surface. The key things to notice in this equation is it's a second order differential equation, and it's singly perturbed with respect to the small parameter that's going to be surface tension, the epsilon squared. The second equation we use to close the system, and in this equation we've got that Hilbert transform, which is an integral you see on the right hand side. This is ensuring that the two variables q and tau are analytic, and this formulation is kind of equivalent to us considering a potential flow problem where we're solving Laplace's equation. We've got some pressure condition on the free surface. And then of course we have three boundary conditions, two in the far field where we want the speed to be 1 because we've non-dimensionalized, and then at the nose of the bubbles at the origin, the speed is 0. And that's because we picked a frame of reference moving with the finger. And this is kind of one of the interesting parts of this problem, is that we've got 3 boundary conditions, but as I said a few moments ago, we have a second order differential equation. So the problem is oversubscribed. What ends up happening is that we need to, this free parameter lambda ends up being selected as an eigenvalue in the problem. Okay. Here, just to complete this kind of initial review of the problem before I move on to the new stuff that we've been doing, I've plotted all the selected lambda values. So I plotted some of the first branches, and these kind of continue up towards 1, if you can use your imagination there. And the interesting thing to notice is that for each of these branches, if we continue towards a small surface tension limit, so when epsilon squared is going to 0, we observe that lambda approaches 1/2 for all of these branches, and that was that value they were finding in the experiments. So all of this work that's led to being able to produce this picture kind of wraps up that problem and resolves some of that mystery before, which was the discrepancy between the experiments and what we were seeing in the analysis. And finally, to motivate what's going to come in the next part, here I've sketched, so this is a kind of artistic impression, but of some of the profiles that we could expect to see on each of these branches. So on the lowest branch, we kind of have this kind of finger that we perhaps expect to see. This is what we see in the experimental picture I showed earlier. And then as we move up the branches, each time we move up a branch, we add an extra small oscillation at the kind of tip of our finger. And this continues all the way up the chain. The interesting thing is that these small oscillations are actually exponentially small. And they're exponentially small in the small parameter, the epsilon squared. So to be able to produce this picture, we need to use some exponential asymptotics to describe what is happening here. And finally, let me conclude this review section by highlighting the fact that in the motivation, I was talking about a tip splitting instability. I've not mentioned that here because tip splitting instability doesn't occur in this channel geometry. To observe that, we need to move to a more general geometry. So this is what's going to come on the next slide. So this is some pictures from some experimental work. This is the same picture I showed you earlier. And to try and capture this tip splitting instability that's occurring, we're going to simplify this geometry slightly to a wedge geometry. So we're kind of taking one of these fingers, but now rather than a straight channel, we allowed it to have some general angle. Oh, that's great. Yeah, maybe a brief.
Okay.
Oh dear. So the USB stick is down 2 pieces. That's a tip split. That's the tip split. That was there.
She split it in half in rage because it
Yeah, that
Splitting instability.
That's right. Yeah.
The red bit is still working.
Okay.
But not this one because it's in my hand.
After a brief interlude, let me remind you, we're now going to consider this kind of wedge geometry. We've got a single finger within a wedge of some angle. So in a kind of simplified picture, we're looking at something like this. So if you don't look too close at what's going on here, it kind of looks at what I showed you before. And then we've got an angle of the wedge, which is going to be a new parameter, theta naught. And now we've got lambda, which appears again, but now lambda is the proportion of the angle of the wedge occupied by the finger rather than the proportion of the width of the channel. Yeah, so this problem formulation has kind of been done by a number of people before me. But what happens in this problem is that as we're injecting the fluid, you can imagine the finger is growing. And over time, the curvature on the sort of end of that finger is changing. So the surface tension is actually decreasing. This is not so easy to deal with. So the resolution here is to rescale the problem. So we end up in a self-similar regime. This is physically relevant after a certain amount of time. And in the self-similar regime, we managed to scale out the dependence on time of the surface tension. So now we've got a new surface tension parameter, which I call the effective surface tension, which is going to be constant in time once we've reached this rescaling. So that's going to be epsilon squared again. And as before, we're going to solve for the free surface profile you'll see on this next slide. So we've parameterized the free surface with parameter zeta. And to do the exponential asymptotics, which I'm going to do to try and produce that bifurcation diagram, I'm going to need zeta to be complex rather than just real in general. So on the free surface, that's this purple line, which corresponds to the purple line there. Zeta is real, and we're going to go into the complex plane. We've got the same variables as before. So we've got a free surface speed and angle, q and tau. And then we've got an extra couple of variables, x and y, which is described in the free surface profile. And then we end up with a set of governing equations, and these look like what we had before, but kind of a bit nastier. The first one highlighted here, is Bernoulli's equation again. So we've got a second order, singly perturbed differential equation. Roughly speaking, there's a bit of a nasty thing going on there. And this is kind of a pressure balance on the free surface. The next equation is the same as before, where we're ensuring that the two variables q and tau are analytic. So this is, you can think of this as being equivalent to doing a potential flow kind of problem and solving Laplace's equation, which ensures analyticity of the variables. And then because the first equation had a dependent on x, now we need an extra set of equations to close the system. And this is just giving us the free surface profile by integrating, in some sense, the speed and the angle on the free surface. Great. So now I'm going to walk through the exponential asymptotics that we've done, which allows us to hopefully produce that bifurcation picture, but for the more general case. The first step here involves an asymptotic expansion in terms of the small parameter epsilon, so in terms of the small surface tension. We're going to shove this into the governing equations. And then we're going to look at what happens at the leading order of that asymptotic expansion. So kind of remarkably in this problem, we can rewrite the leading order in terms of these two equations, which don't have an integral in them anymore. I'm not going to claim any of this as my work. This is thanks to these two people that we've got this nice form, which is somewhat surprising to me that it turns out so nicely, but it makes our life a bit easier in this step. So we've got these two equations, and even more remarkably, we can actually write explicit solutions involving some hypergeometric functions. That's what the capital F's are. So that makes our life easier in this step where we're trying to solve the leading order problem. In some other problems that we do, we don't have this nicety and we have to solve it numerically. This is my slight shout out to Jean-Marc, is that in these types of problems, we often end up using your numerical schemes to solve this leading order problem. Yeah, so we've solved the leading order problem on the real zeta axis, so it's on the free surface. You remember in the far field, our solution is going to 1, and at the origin it's 0. This is the leading order speed. Okay. So the next step is we're going to analytically continue into the complex zeta plane. So zeta is real, now we're going to allow it to be complex in general. This sounds a bit scary if you've not encountered it before, but we've got a set of differential equations here. We've got an initial condition on the free surface. We're just going to use your favorite ODE solver in MATLAB and just walk along some path into a complex plane solving these equations using that initial condition. And we can do that along lots of different paths, and we can mesh out the whole plane. That's this grey surface you're seeing. What we're interested in finding in this complex analytic continuation is the locations of any singularities that occur and their strengths. So here you can see that if we follow the black path, we bump into a singularity. By kind of walking towards the singularities and observing the behavior, and also by analytically continuing around singularities and understanding their sort of branch behavior, we can identify their locations and their strengths with some numerical accuracy. So that's what this step involves. We understand all of that, and then we move on to the next step. So this was meant to come up one bit at a time, so just pretend that bit's not there yet. But the leading order solution, one of the singularities lies at zeta star. This is a square root singularity. So when we get close to that singularity in the complex plane, the leading order solution has this sort of behavior. Now, Bernoulli's equation was a singly perturbed second order differential equation. So when we try and solve for the next order, we end up having the next order being approximately 2 differentiations of the previous order. So if I differentiate this twice, stuff pops out and the strength of the singularity increases. The next order, the same thing happens, and hopefully you're starting to observe a pattern. And we can write down a general ansatz for what an nth order term would look like. So here we've got on the top a capital Q. This is some prefactor function, which is not so important. We've got a gamma function, and this gamma function is taking care of all of the numbers up popping out the front when we're differentiating. This is basically a factorial, but we're using a gamma function because these are not necessarily integers. And on the bottom, we've got a chi, which is what we call the singulant function, and that's encapsulating the singular behavior. This is a chi that we've derived for this problem. It looks horrible, but what I'd like you to take away from this is that chi is 0 at the singularity. That's essential for this behavior to be encapsulated by it. If we're at the singularity, we're integrating from zeta star to zeta star. And also, we've got a horrible term here, but all of the variables and stuff in this term, we've got analytic continuations of them from the last step in the complex plane. So in principle, we can combine them all, we can integrate them in the complex plane, and we can also find chi everywhere in the complex plane if we wanted to. Great. So now we move on to the next step. This is what I showed you before, the factorial over a singulant type behavior. And this is a key part of exponential asymptotics, is that this, if we plot successive terms in the asymptotic series, then we get a picture which looks something like this. At first, the epsilon is small, so the terms are getting smaller and smaller at each step, but at some point, this factorial behavior on the top is blowing up and it starts dominating. So at some point, the terms in our asymptotic series are reordering, and that's not really very good. So our resolution is to truncate the asymptotic series before this gets too bad. You can kind of see from the picture that the optimal place to truncate it is when 2 of the points are approximately the same size. That's when we've reached a minimum. Using that condition, we can find what capital N needs to be. The capital N is an integer. That's why I've added on a beta to ensure it's an integer. It's just some small number. And it depends on epsilon. So capital N gets larger when epsilon gets smaller. We take more and more terms in our series, but we always truncate it at some point. And here I've truncated all of my variables. This means that our actual solution is going to be the truncated asymptotic series plus some remainder term. And the key part of exponential asymptotics is that when we've done that optimal truncation, then the remainder term ends up being exponentially small. And in this problem, it has this form here. We've got a capital A, which is a Stokes multiplier, which is a kind of three-factor multiplying the thing. This is a capital Q from before, which is some function. And remarkably, this chi, the singulant function, pops up again in the exponentially small term. Okay, we're nearly there. So now we want to analyze these exponentially small terms. So what happens is that the Stokes multiplier A, which is the prefactor multiplying the remainder term, can be either really, really small or kind of algebraically big. And it's switches kind of size. We say it's like switched on when we cross one of the Stokes lines in the complex plane. And it turns out that the Stokes lines are defined by this real part of chi being positive and the imaginary part of chi being 0. So previously I told you that we can in principle find chi everywhere in the complex plane. So we can just go and check when the imaginary part of chi is 0, when the real part of chi is positive, and we can plot the Stokes lines. So I've gone and done that. And we get something that looks like this. I'll just talk you through it. So we've got the complex zeta plane. On the real zeta axis, that's a purple line, we've got the free surface. And then we've got 6 black crosses, which are the singularities in the complex plane. So kind of 3 complex conjugate pairs like here. And since the singulant function is 0 at the singularities, these singularities are kind of the ends of the Stokes line. In black, I've plotted each of the Stokes lines, and from each singularity, a Stokes line emanates. From these two, we've got Stokes lines that come around like this. And then we've got a kind of symmetric looking thing. And then in the center, we've got a Stokes line that goes down the imaginary axis. The gray surface is me trying to kind of visualize what the Riemann surface looks like, because we've got branch cuts at plus and minus I. And if you just take one thing from this picture, it should be this, that there are 3 points where a Stokes line is meeting the 3 surface. So if some exponentially small remainder term is being switched on or switched off when we cross a Stokes line, then there's 3 points where that's happening in our free surface solution. And this now allows us to derive the selection mechanism. Okay, so here, so again, the darker purple is the speed on the free surface. So we've got the real zeta, we've got the real part of the speed. In the far field, it's going to 1, and at the origin, it's 0. In the far field, it needs to be 1. So here we can't have any exponentially small remainder terms, any exponentially small oscillations in our solution, or we wouldn't be satisfying that far field condition. So remainder term must be 0 from the far field up to this point. Then we cross the Stokes line. When we cross the Stokes line, we switch on one of the exponentially small terms. That looks like this. We get some exponentially small oscillations in our solution. Then at some point we cross another Stokes line, we switch on another exponentially small remainder term. These kind of add up to give us some sort of pattern. And then at the third Stokes line, we switch on another set. This is all great until we get to the far field condition where we wanted our solution to be 1. So if we want the solution to be 1, all of these exponentially small terms must somehow cancel out to be 0. And this is our selection condition. This is what's going to give us that bifurcation diagram. A final thing I'd like to highlight before we move on to the bifurcation diagram is this kind of picture. So the 2 Stokes lines on the left and the right are kind of symmetric. So chi1 and chi3 kind of somehow symmetric versions of each other. Hopefully you could see that from the Stokes line picture before. The central Stokes line is a bit different. So I'm kind of interested in the relative sizes between chi1 and chi2. And I'm interested in that because when we've got something that's e to the minus chi over epsilon, when chi is positive but small, that's going to be a larger thing than if chi is very positive but very large. So here I've plotted the relative sizes of the real part of chi. And when lambda is smaller, then the real part of chi2 is smaller, which means that this central term is dominating. When that's happening, if these other terms are subdominant, it's quite hard for this thing to be 0. However, when we move further up here, then that central term is now subdominant, the other terms are dominating, and it's easier to cancel out two things that are kind of symmetric, the plus and a minus, for example. This is a picture for theta naught being 20 degrees. If I make theta naught smaller, then this crossing point moves further to the left. And when theta naught is 0, so that's the channel geometry, then this purple line lies at infinity, and we've only got the left and the right Stokes line interacting with each other. So let me conclude with the kind of grand finale of the different bifurcation diagrams. Some of the numerics here still need to be completed, so hopefully you can use your imaginations. But on the top left, I've got the bifurcation diagram I showed at the start for the channel geometry. And here I've got 3 bifurcation diagrams for different wedge angles. You'll notice the most obvious thing to notice here is that the branches close off when theta naught is not 0. And that's occurring because, as I showed you on the last slide, when we had the intersection point, different parts of the exponentially small stuff is dominating, and the selection mechanism at some point stops being able to be satisfied. Another thing to notice is that, for example, the first branch and the second branch close off at smaller and smaller epsilon values as theta naught increases. And finally, we think that this closing off is what's creating that tip splitting instability we see in the original picture I was showing at the start. So in the original picture I was showing at the start, I was saying that we have a full circular geometry, we're chopping out some wedge which has a single finger in it. That finger propagates and the curvature decreases, which means that the surface tension kind of in reality is decreasing in time. So we have some branch which is a solution, and then in reality we're moving left along this picture. At some point, the selection mechanism can't be satisfied anymore. We think this is the point where that single finger is forced to split into 2 smaller fingers, which would then have half the wedge angle. And then we jump onto the next picture here and we continue. Thanks for listening. I hope you found that interesting. I've taken the time.